Master chemical reactions and equations in just 10 minutes. Let's begin.
Hey everyone, and welcome to another Explainer. Today, we are targeting your board exams with pinpoint accuracy. We're tackling the very first chapter of CBSE Class 10 Science, Chemical Reactions and Equations. We've essentially taken this entire NCERT chapter and distilled it into a super clear, step-by-step visual journey. Our goal, maximum concept clarity with zero distractions. So get ready, because we're about to master the language of chemistry.
Okay, let's dive right into this. Here's our roadmap for today. We're going to start by figuring out what chemical reactions actually are. Then we'll tackle balancing equations, which is super important. After that, we'll break down combination, exothermic, decomposition, and displacement reactions. And finally, we'll wrap the whole thing up with a rapid revision and some absolutely crucial exam tips. Let's do this.
All right, Section 1. What are chemical reactions? To really get this, we need to put on our detective hats and look for clues of chemical changes happening right in front of us.
I mean, think about this for a second. What actually happens when milk is just left out at room temperature during the summer? Or when food digests inside our bodies? I'll let you pause and really visualize that. In all of these everyday situations, the initial substance doesn't just, look a little different. Its fundamental nature, its actual identity, is permanently changed. And that permanent shift? That is the absolute hallmark of a chemical reaction.
Now, to really speak chemistry, we need the right vocabulary. The substances that go into a chemical change, like magnesium and oxygen here, are called your reactants. You'll always find them sitting on the left side of your equation. The completely new substance that gets formed, like this dazzling white magnesium oxide powder, is your product, which sits on the right. And that arrow in the middle, it just points from reactants to products, showing us exactly which way the reaction is going.
So, as detectives, how do we actually prove a reaction occurred without, say, a giant microscope? Well, we look for clues. As you can see right here, there are four main pieces of scientific evidence we look for: a change in state, a change in color, a gas being released, or a sudden change in temperature. If you spot even one of these, like a test tube suddenly getting hot or bubbles forming out of nowhere, boom, you've got a chemical reaction on your hands.
Okay, moving on to Section 2, balancing chemical equations. We've got the vocabulary down, but now we really have to learn the grammar rules of chemistry. And we absolutely must balance our equations to satisfy one of the fundamental laws of the universe.
Which brings us to a massive board alert. The law of conservation of mass literally states that mass can neither be created nor destroyed in a chemical reaction. So what does that actually mean for us? It means the total mass, and therefore the exact number of atoms for every single element, has to remain exactly the same before and after the reaction. You can't just magically lose an iron atom, and there's no way you can just invent an extra oxygen atom out of thin air.
Now, what's really interesting about this slide is how clearly it exposes an unbalanced, or what we call a skeletal, equation. We're looking at iron reacting with water here. Just look at the table. On the left-hand side, we only have one atom of iron, but on the right, we suddenly have three. Oxygen is totally out of whack too, with 1 on the left and 4 on the right. So this equation is currently breaking the law of conservation of mass. We absolutely have to fix it.
And to fix it, we use the hit and trial method. Think of it like a logical puzzle. Step 1, draw clean boxes around each chemical formula. Step 2, list out all your atoms, just like we did. Step 3, and this is a pro tip, always start balancing with the compound that has the maximum number of atoms. It makes the whole puzzle so much easier to solve. And finally, Step 4, do a final head count to check your work, and add in your physical state symbols, solid, liquid, gas, or aqueous.
Wait, before we move on, I have to highlight a really crucial exam tip. This is literally where students lose marks every single year. When you draw those boxes around the chemical formulas, you have to treat them as impenetrable brick walls. Do not alter anything inside the boxes. You can only balance the equation by placing whole numbers, coefficients, on the outside of the boxes. Never ever change H2O into H2O4 just to balance your oxygen. You'd be turning water into a completely different, probably toxic chemical.
All right, Section 3, combination and exothermic reactions. Now that we know how to balance equations, let's start classifying them. We'll kick things off with reactions where substances join together and, a lot of the time, release a massive amount of energy while doing it.
So, by definition, a combination reaction is exactly what it sounds like. Two or more reactants combine to form one single product. For example, when solid calcium oxide, which is also known as quicklime, reacts vigorously with water, the two combine to form a single product, slaked lime, or calcium hydroxide. And fun fact, if you were to touch the beaker during this reaction, it would feel incredibly hot to the touch.
And that heat brings us straight to our next concept, exothermic reactions. These are basically reactions where heat is released right alongside the products. And this brilliantly illustrates how textbook chemistry connects directly to your daily life. Just take human respiration. The glucose from your food actually combines with oxygen in your cells, releasing the vital energy your body needs just to survive. Respiration isn't just breathing in and out. It's literally a life-sustaining exothermic chemical reaction happening inside you right now.
Moving on to Section 4, Decomposition Reactions. If combination is all about bringing things together, what do you think happens when we tear them apart? Let's find out.
I want you to imagine a large, complex molecule breaking apart into multiple simpler pieces. That right there is a decomposition reaction, a single reactant breaking down to give simpler products. But here's the catch. Because breaking chemical bonds requires energy, these reactions almost always require heat. When we use heat to force the molecule to split, we specifically call it thermal decomposition.
And hey, we have another highly testable board alert right here. When you heat ferrous sulfate crystals, you will physically see their green color change, and you'll actually smell the very distinct, sharp odor of burning sulfur as sulfur dioxide and trioxide gases are released. And what about when you heat lead nitrate? Well, it produces these super distinct, thick brown fumes. Those brown fumes are nitrogen dioxide gas. You definitely want to memorize those specific color changes in gases for the exam.
Okay, Section 5. Displacement reactions. We've seen things join together, and we've seen them break apart, but now let's look at what happens when a more reactive, aggressive element steps in and just totally takes over.
Just take a look at this classic lab activity. Before the reaction, we take a shiny iron nail and drop it into a vibrant blue copper sulfate solution. After waiting about 20 minutes, a total elemental takeover has occurred. Iron is actually more reactive than copper, so it literally kicks the copper right out of the solution. That displaced copper coats the nail, making it look brownish, while the solution itself actually fades from blue to green, because it's now iron sulfate. Wild, right?
But wait, what if both reactants swap partners? Well, that's called a double displacement reaction, an outright exchange of ions between the reactants. A perfect textbook example of this is mixing sodium sulfate with barium chloride. When these two totally clear solutions mix, they instantly swap ions and form this white, chalky, insoluble solid called barium sulfate that just settles right at the bottom of the test tube. By the way, any reaction that produces an insoluble solid like that is also known as a precipitation reaction.
All right, we made it to Section 6, Rapid Revision and Exam Tips. Let's move to the final mastery phase and see how all this builds together. You've absorbed the core concepts today, now it's time to lock them in for the boards. Check out this incredibly clean revision formula box. Honestly, take a mental snapshot of this right now. Combination is simply A plus B makes AB. Decomposition is the exact reverse. AB breaks down into A plus B. And displacement? That's when A plus BC becomes AC plus B. Structuring these concepts abstractly like this makes the actual chemical equations underneath so much easier to digest and remember on test day. Now I want to put on my mentor hat for just a second. Please look at this common mistake warning. Year after year, I see brilliant students perfectly balance a massive equation only to lose an easy half mark because they just forgot to write the physical states. So always double-check your final answer. Did you include the small s for solid, L for liquid, G for gas, and AQ for aqueous? Those tiny little details are exactly what make your chemical equations scientifically accurate and board ready.
So, to wrap things up, I'm going to leave you with this classic NCERT exercise question to really test your newfound understanding. Why should a magnesium ribbon be cleaned with sandpaper before burning in air? Think about what might be coating the outside of that metal and why that layer might interfere with a clean combination reaction with oxygen. I highly encourage you to review the chapter, test out your balancing skills, and confidently tackle this question. Keep learning, stay focused, and you are absolutely going to crush your science exams. See you on the next explainer.